This is Unit 3 Practice Exam B for Math 1100. Question 1, this is from Chapter 4. You need to remember the rule for differentiating logarithms. Natural log, rather, would be 1 over u times u prime. Now, what I'd recommend is you do rules of logarithms first. So this is 2 times x squared, which means it's a product. So you can use a product rule and separate this into the sum of 2 logarithms. And then you can take that exponent of 2 and move it down to the front. So once you've simplified the logarithmic expression as much as you can, then I would differentiate. So the derivative of natural log of 2, this doesn't actually need the rule for logarithm differentiation because it's not a variable expression. Natural log of 2 is a constant expression. It's like differentiating 5 or negative 6. The derivative of a constant is 0. So we really only need to worry about differentiating this term. 2 is a coefficient, so it's going to stay 2. The derivative of natural log of x is 1 over x, so it's 2 times 1 over x, which is 2 over x. Question 2, the rule for differentiating base e exponential is the derivative of e to the u is e to the u times u prime. So the derivative of y with respect to x of e to the u is e to the u times u prime. Question 3 is obviously not a natural log, so it's not going to follow the same rules necessarily yet as we did here in question 1. So what we're going to do if you have a logarithm with a different base is use what we called the change of base formula from Math 1050. So we're going to change it into a natural log. So it's the natural log of 2x to the 5th divided by the natural log of 4. And then I would move that natural log of 4 rather than as a denominator, use it as a coefficient. And then simplify this logarithm here, kind of like we did here. So this can simplify since we're expanding this with a coefficient. So that coefficient needs to be put in front of a parenthesis when we expand. So that expansion of this logarithmic expression is just natural log of 2 plus. Now it's going to be the natural log of x to the 5th, but I'm going to go ahead and move that 5 down in front. So now when we do a derivative, if we imagine that this were distributed to that, it's the natural log of 2 divided by the natural log of 4. Both of those are constant values. Natural log of 2, natural log of 4. There's no variables there, so the derivative of a constant is 0. So this times this, the derivative of that is 0. This is going to multiply here. So the 5 is going to multiply with this 1 over natural log of 4, so that becomes 5 over the natural log of 4. And then the derivative of natural log of x is 1 over x. So we have 5 times x times the natural log of 4. Now question 4. The exponential expressions that don't have a base e follow a slightly different rule. So if you're differentiating e to a power, then the derivative is just e to that power multiplied by the derivative of that power. If you have another base, like a base 2, then this formula applies. So the derivative with respect to x of a to the u, so now this is not e to the u, it's a to the u, where a is just a constant value besides e. The derivative is the natural log of a times a to the u times u prime. So if we use that formula for this, And then we're going to have the natural log of 2, because we're a base 2 exponential here, times 2 to that power, 5x to the third, multiplied by the derivative of that power, 15x squared. And there isn't a real defined order that those terms need to go in, so you're fine just to leave it like that. There's nothing really to simplify there. Question 5 and 6 are meant to help you with two things. There are exponential expressions, so you need to remember how to differentiate base e exponentials, but then we're going to use other previous rules of differentiation, like the quotient rule here or the product rule here. So for question 5, obviously that's a quotient rule. So we have the bottom function multiplied by the derivative of the top function. So the derivative of e to the x squared is e to the x squared multiplied by the derivative of x squared. Now minus the top function multiplied by the derivative of the bottom function, which is 20x to the third, divided by the bottom function squared. Now, considering the numerator, are there any common factors between, so if we have the minus sign here, that means we have a left side and a right side, so a common factor could be e to the power of x squared. And also, if we consider 20x to the third and 2x becomes a common factor. So I'm going to factor out from the numerator a 2x and then an e to a power of x squared. So then from here, I factor out the 2x, I factored out the e to the x squared, so that just leaves 5x to the fourth plus 4. And then from here, I factored out e to the x squared. I factored out 2x from 20x to the third, so that's going to leave a 10x squared. And that's about as far as we can simplify that one. Question 6 is going to use the product rule. So we have two factors here, this product, that factor times that factor. So if we call that one f and g, then the derivative is f prime times g plus g prime. So the derivative of e to the 2x squared is e to the 2x squared multiplied by the derivative of 2x squared, which is 4x. So we have f prime times g plus g prime. So we need to multiply that by f. Now again, common factors. We have a common factor of e to the power of 2x squared. And between 4x and 6x squared, we can factor out a 2x. So I'm going to factor out a 2x and then e to a power of 2x squared. From this side, that's going to leave a 3x. From this side, that's going to leave a 2, and then that term right there. And then if we simplify by distributing that 2, we're going to have a 4x to the third plus 3x plus 6. For question 7, I would definitely simplify that logarithmic expression before taking a derivative. So if we apply the power rule first, And then we use the quotient rule. So that 4 is going to stay a coefficient for both logarithms. And then I'm going to also go ahead and expand that because we have a product 2 times x to the third. And that 4 is going to be a coefficient of both of those. So 4 natural log of 2 plus 4. Well, the 3, I'm also going to use the power rule and move that 3 down in front to multiply with what would have been a 4 there. So 3 times 4 is 12. So that's going to be a 12 natural log of x minus 4 times the natural log of 5x to the fifth minus 2. That's fully expanded. It's about as simplified as those logarithmic expressions are going to go. So now, if we consider the derivative of each of those terms, the derivative of 4 natural log of 2, that's a constant expression. So the derivative of a constant is 0. The derivative of 12 natural log of x, the natural log of x turns into 1 over x. 12 times 1 over x is 12 over x. And then the derivative of 4 natural log of 5x to the fifth minus 2 is going to be 4 as a coefficient, and then 1 over 5x to the fifth minus 2 multiplied by the derivative of 5x to the fifth minus 2, which is 25x to the fourth. If we simplify there, we end up with that. The phrase we're looking for here in question 8 is this one right here. It grows at a rate proportional to its population. So that phrase again tells us it follows the exponential growth model, where y is a future amount, c is an initial amount, k is the relative growth rate, t is an amount of time. So 6.1 years ago, we had 1,517 as a population. So if we consider that as an initial population, then currently we have 1,800. So it grew from 1,517 to 1,800. We weren't given a relative growth rate, but it took 6.1 years for this initial population to grow to that size. So we put 6.1 in for t. Now we got to solve for k. So we isolate the exponential term by dividing that coefficient. Then use natural log to cancel the base e exponential. If we use a natural log here, then the e is going to cancel with the natural log, leaving k times 6.1. So the value of k that's the exact form of k. We're going to want an approximate form also. So the approximate form is 0.028. So now that we have the relative growth rate, the actual question is, what will the population be in 7.5 years? So we can go back to this model. So if we're talking about present time, we can consider the initial population. If we're starting now as time 0, the initial population would be 1,800. In 7.5 years, what's the future population with this relative growth rate here? So if we say what's the future amount y when initially we have 1800 with a relative growth rate of 0.028 for 7.5 years. And that would be approximately 2,221. Now, we're talking about a population, I'm assuming, of people, but it could be a population of animals or something on this island. So it would not really make sense to do 221.2 or point whatever of a physical thing, like a person or an animal. So we're just going to round down to a whole number, 2,221. These two questions, 9 and 10, these are from chapter 7. 9 is from 7.4. 10 is from 7.5. So in 7.4, what we were just practicing is finding the first partial derivatives. So we need the first partial derivative with respect to x. That's when we regard y as a constant value. So if y squared is just a constant value, it's pretty much like 6. It doesn't get differentiated. We differentiate the variable expressions. So the derivative of x with respect to x is 1, leaving the constant expressions multiplying each other, so 6y squared. Here, the 2 and the y cubed are the constant expressions, so we're differentiating x squared. The derivative of x squared is 2x. So the 2x would multiply the other constant expressions, 2 and y cubed, so 2 times 2 is 4, so minus 4x y cubed. Here we have the derivative of 4x cubed with respect to x. That's going to be 12x squared. And then the derivative of 4y is a constant expression. The derivative of a constant is 0. Now the other first partial derivative is with respect to y. So now x is the constant expression. So 6 and x are constant expressions. They're just coefficients. So we differentiate y squared. Y squared is 2y. The derivative of y squared is 2y. The 2 would multiply the 6 and the x. So we get 12x times y. This time around, if y is what we're differentiating, then x is the constant. So 2x squared is a constant. So we're differentiating y cubed. The derivative of y cubed is 3y squared. The 3 would multiply with the 2, making a 6. The derivative of 4x cubed, this is a constant value, so it would be 0. The derivative of 4y is 4. Now for question 10, this is from 7.5. There were some formulas that are needed. You need to use these formulas. I'm not going to require that you memorize them. The first one is once you take your first partial derivatives and set them equal to 0, that's going to give you a critical point. Now you have to determine whether that critical point is a minimum or a maximum or neither. That's determined by the value of d. So d is second partial derivatives. So it's the product of this second partial derivative multiplied by this second partial derivative minus the square of that partial derivative. So that's d. And then, like I said, depending on the value of d and the value of this second partial derivative, that will determine whether your critical point is a minimum or a maximum or neither. We call that a saddle point. So if d is greater than 0 and this second partial derivative is greater than 0, it's a minimum. D is greater than 0, but that second partial derivative is less than 0, it's a max. If D is less than 0, then it's a saddle point. So we need to find the first partial derivatives, both of them. So with respect to x, we're going to have 2x, that's going to be 0, plus 2, that's going to be 0, and that's going to be 0. So it's 2x plus 2. For y, that's going to be 0. That's going to be 2y. That's going to be 0. That's going to be minus 6. And that's going to be 0. So it's 2y minus 6. Now we have to set those equal to 0 to find a critical point. So this one's going to give us x equals negative 1. This will give us y equals 3. So there's a critical point, negative 1 comma 3. Now we need to figure out the value of d. Before we do that, though, we need some second partial derivatives. So if we do a first partial derivative with respect to x, that gave us this expression. If we do another partial derivative with respect to x, this is going to give us a 2. That's going to give us a 0. So that's 2. Now the first partial derivative with respect to y gave us this expression. If we do another partial derivative on that with respect to y, that's going to give us a 2 minus 0, which is 2. Now if we do a first partial derivative with respect to x, that gives us this. If we do another partial derivative with respect to y, that's going to be 0. That's 0. 0 plus 0 is 0. So now d is equal to this second partial derivative, 2, multiplied by this second partial derivative, which is also 2. So 2 multiplied by 2 minus this partial derivative squared, which is 0 squared. And that's equal to 4. So from this, we conclude that d is greater than 0. That second partial derivative was also greater than 0. So it means it's a minimum value. Now, this critical point is just an x and a y number, but the function itself is a function of 3 variables, x, y, and then f of x, y is really z. So there's 3 variables, x, y, and z. We're supposed to find the relative extrema, meaning the point on the graph. This is a graph in 3-dimensional space, so we need a point with all 3 dimensions, x, y, and z. So to find the minimum point, we know that it's a relative minimum. At an x value of negative 1, a y value of 3, to find the z value, we just plug in a negative 1 for all the x values. We plug in a 3 for all the y values and evaluate. So negative 1 cubed is 1, 3 squared is 9. This is negative 2, that's minus 18, and a plus 6. So 1 plus 9 is 10. 10 minus 2 is 8. 8 minus 18 is negative 10. Negative 10 plus 6 is negative 4. So the relative minimum point on the graph is the point negative 1, comma 3, comma negative 4.